Hey, welcome to this stream, everyone. In this stream, we are going to continue building Nand2Tetris projects. So today we are going to create a CPU chip. So let me open up the slides. Where is it? And these are the slides. So this is the basic interface of a CPU that we are going to build. It will have 3 inputs and 4 outputs. But there's a lot going on inside the CPU, and this is the diagram. Basically, we will have to implement all of these things. Although it seems that we are given all the connections, if you look carefully, this control bits are just a placeholder for different control bits which are present inside these individual chips. So we will have to figure out a logic how to connect all these control bits, and there's a lot going on, so I'm sure this is going to be a long stream. Alright, then let me open up the HDL file of this CPU, then we will see what to do next. Where is it? CPU HDL, CPU dot HDL. What is it? CPU external? Well, doesn't matter, we'll see it later. Beam CPU dot HDL. So we are given 3 inputs. Input AM, which is, what is it? Input AM contains of RAM, okay, which will be of 16 bits. Instruction again of 16 bits. A reset bit, which will be either 0 or 1. Output AM, write AM. Output AM is of 16 bits. Write AM 1 bit. Address AM 15 bits, and program counter of 15 bits. So I think first we should get all these chips directly, and we'll check the logic later. So let's get Mach 16 first. It's just a simple mux with 16-bit inputs and 16-bit output. So it will have, so first of all, let's check out this mux. Mux 16. So it will have 3 inputs, 1 output. All right. Selector bit is of 1 bit only, and we will have to see. So that's where this control bit goes. We will have to, okay, we'll see it later. First of all, let's provide the input. First input will be, well, there are 2 inputs going inside mux. First input comes from this output M. This will directly go inside first input, and second input is instruction, which is this one. So I guess we can directly pass it or maybe not, we'll see later. So if I pass output M as the first input and instruction as the second input, and then we will have to take care of this selected bit as well, but we don't know yet what we should be passing to this selected bit, so we will keep blank, keep it as blank for now. And we also have output, can I guess let's call it mux output. No, mux O1. Yeah, this will be an apt name. So I'm going to keep the implementation of mux chip incomplete for now. Let's get another chip which is a register. Okay, we don't have a register, right? A register is just a simple register. Let me check if we have such a register inside built-in chips or not. A register. Okay, we do have a register now. What's special about a register? Why can't we just use a simple register? Let's check this HDL file. Well, it just looks like a simple register. It has an input of 16 bits, a load bit and output bit. Then why have they given it as a different register? Okay, it simply has the side effect of providing a GUI representation. Okay, it seems there's no difference between a simple register and a register, but anyway, it is called a capital R register. So let's import it inside our HCL file. A register, it will have input of 16 bits, and this input will come from mux O1, and output, for output, first let's get the load bit. Now again, we don't know what to pass to this load bit, so we'll keep it as blank for now, and we'll pass the output inside an intermediate variable. Let's call it areg O1, and we don't need 1 in this case, so we'll keep it as areg O. Now let's get a mux 16 again. So let me copy this one. So this mux is for this chip. So this mux has this input. One input comes from this A register and another input is input M. Alright, so first input will come from A register, which is this one, A reg O. Alright. First input comes from A register, second input is in M, which is this one, in M. So let's get rid of instruction and pass in M. Cool. And for the selector bit, again we'll keep it as blank, and output, let's call it mux O2. Now let's get this D register. So I guess we also have a D register as a built-in chip. Yeah, we do have a D register. Let's also check the implementation of D register just to make sure it is same as A register. Yeah, it is same. So let's import it inside the file. I'm gonna copy this A register only. This is D register, alright. And the first input, not the first, the only input will be coming from ALU output. Well, okay, it's just output M. So it's just this one. We should pass it over here. Output M, correct. And again, we'll keep load bit blank, and we'll pass the output to dreg-o. And now we'll get this program counter. Let's get the program counter first. Just PC, I guess. Let me recheck it. Yeah, it's just PC. PC.hdl. It will have 16-bit input, a load, incrementer, reset, and output. I hope you guys can hear me. I have turned on the music. Alright, so where was I? Okay, I was checking out this program counter. It has a 16-bit input, load, incrementer, reset, and a 16-bit output. So a 16-bit input, it will come from this A register, right? Yes, it is coming from A register. So the output of A register is inside A reg O. Now it should be A reg O. We also have we have a load, increment, and a reset bit. So for load bit, let's keep it as blank. Increment blank again, and reset bit. We can directly pass this reset bit which we have inside the CPU. It is this is the reset bit, right? We are passing it directly to this program counter. Now What else do we need to pass? Output. Output, let's call it PCO. Although we can directly pass it to this PC, this PC15. So let's pass it to PC, but this is of 15 bits, and I guess this program counter has 16-bit output, but we are only given a 15-bit PC output, and I have they given only 15 bits. Is this program counter of 15 bits only? I mean, the input is of 16 bits, right? Or is it? Well, of course it is of 16 bit. We also have a 15-bit address M, which is this one, I guess, memory address. Why have they given a 15-bit program counter output? Okay, this is why, because we only need 15 bits to address this RAM, the whole address space of RAM. So that's why we are only given 15 bits. Okay, but which 15 bits we are going to pass? This is problematic. Which 15 bits we are going to select from this A register? Should I pass 0 to 14 or 1 to 0 to 13 or 1 to 14? Should I get rid of the 0th indexed bit or the last bit, or is it the last one? I was confused about the order of the bits inside the memory previously as well. Well, for now, let's see, for now I'm just going to keep 0 to 15, 0 to 13. So I'm going to get rid of the last bit, apparently, which is the 14th bit. As this output is of 15 bits, the last index will be 14th, and we will need to get rid of it. We forgot to write 13 over here. We are only going to select 0 to 13 bits, and we are going to get rid of the 14th bit, and we will pass it to this program counter. All right, we have this thing now. What do we need to do now? Okay, we have got the program. Now let's get the ALU chip. ALU. Now this chip is a little complex, so we'll have to check how it is implemented. ALU. So as you can see, now we don't know what we have to pass to all of these control bits. We only know that these two inputs will be coming from either from D register or this Mach16, and we also know where this output bits will go to. So let's write the implementation of those bits only for now. X and Y. So X will be coming from D register, and output of D register is inside, where is it? D reg O, and the output, the input of Y will be coming from this Mach16, which is the second mux. So mux O2. Now we're going to not worry about the control bits, but let's write them anyway. So we have ZX, NX, ZY, NY, F, and no. ZX, ZX, NX, and ZY, NY. ZX, NX, ZY, NY. Right, and F, NO. F, no. And what else do we have? We have this output flag ZR and NG. We will write it at the last. We also have output. So for the output, we will pass it to directly to this output M. In the figure, they are directly passing it to output. But we also need this output inside this Mach16 and also inside this D register. So for that we can't directly pass it to output M. We'll keep it inside an intermediate variable. So we'll call it ALU. Yeah, right. And we also have ZR and NG. For ZR and NG 0 and negative. ZR and NG. Okay, so now we also need to get this ALU 0 inside output M. So let's pass it to output M. We'll use, let me think, we can use AND 16, and for the first input we can pass ALU 0, ALU, and we'll keep second input as true, and the output will go inside output M. Good, so now we have got the output inside output M as well. Now we need to get the same output inside D register and our mux as well. So we will pass D register wait. We are directly passing the output M to this chips. So can I also directly pass this output to output M? Let's see. Output M. So for now, let's comment out this code. We'll see if this thing doesn't work. If if the HDL simulator gives us error about this output, then we will uncomment it and try to implement another logic. Okay, so now what we need to do? I guess this is it for inputs and outputs. Now wait, we also need to get output inside this address M, and the output of the input of address M comes from this A register. So we can do, well, we can use a N16, right? And for the first input, we'll pass the output of A register, which is inside A reg O. B will be true, and output will go inside address M. Okay, what else do we need? We have output inside output M. We also need to provide this input to write M. But first of all, we will have to figure out the logic for this control bit. So we'll do it later on. We have input inside address M and the program counter as well. And we have used this int M reset and instruction inputs as well. So let's see now. Now comes the hard part. We have to figure out the logic of this control bit. So I guess we should start with this control bit for this mux16. So let's see, it is of just a 1 bit. So, and this 1 bit, now what does this mux16 do? It takes either instruction or the output M as 2 inputs. So based on this bit, it should either select this instruction or the output to pass it to A register. Now where does this control bit come from? So we want to load the instruction inside A register. Okay, this instruction is, wait, oh yeah, it is this one. Instruction is that of 16 bits, 3, 4, 6, 10, 10, 16. Yeah, it is of 16 bits. Okay, so when should this A register contain instruction or the output M? What is output M? It is the output coming from ALU. Now what does it contain? ALU contains the output. Now what does this output contain? It is the result of the computation that we do on these two inputs, X and Y. All right. So this is, let me check other slides. There was mention of this cycle called fetch and execute, I guess. Where is it? Fetch and execute. Yeah, it is this one, I guess. Or not. Executes a hack instruction and figure out which instruction to execute next. Discussed before. Where is it discussed? Okay, it is over here. This is for program counter, I guess. We need to check it for this part. which is over, I guess it is over here. Okay, this part. So the A instruction comes in. Okay, this is just an instruction which happens to be an A instruction, and we pass it to this second input. Now how is this instruction handled? This is the opcode which tells us if it is an A instruction or C instruction, which is the computation instruction. Okay, and a 15-bit value. This 15-bit value stores the value inside the A register, outputs the value not shown in this diagram. And if it is a C instruction, decodes the instruction bits into opcode, ALU control bits, destination load, and jump bits. Routes this bit to that chip part destination. Okay, what does it mean? So now this bits consist of different bits. First we have ALU bits. These are ALU control bits. Now what are these 3 bits? 2 bits, I mean. Let's check out what this 2 bits represents. We are on slide 39. We'll get back to it again. So it is inside. Well, it must be inside chapter 4. Yeah, it is over here. Mnemonics. Where is it? This is the opcode and not used. Yeah, these are just placeholder bits. They don't mean anything. All right. But do they mean anything in? Yeah, they means the value. So these 2 bits are used in case of A instruction. So these 2 bits will be the part of the value which will be set as A register. But in case of a C instruction, we are not going to use these 2 bits. So let me get back to slide. We were on slide number 39, I guess. So this is the opcode. We are not going to worry about these 2 bits in case of C instruction, and the bits after this 2 not used bits are ALU control bits. So we will have to route these bits to this ALU. which will go inside this bits. So we'll see, I check it out later. And these 3 bits are destination load bits. Okay, what does it mean? Okay, so where do we want this bits represents where we want to load the computation. So for this, I mean D. And last 3 bits are for jump instruction. Input 1 from D register. Is it? Okay, yeah, it is from D register. Where is D register? It's over here. Well, we'll see about this other bit. First, I was thinking that this first bit opcode 0, it is either 0 or 1. So in case of 0, it is an A instruction, and if it is 1, then it's a C instruction. Now if it is an A instruction, we want to load this value, this 15 bits inside A register, right? So now this A register takes in let me check the register implementation. So it is of 16 bits, but we have to pass only 15 bits to it. So that means we can use this first bit from the instruction as this control bit. So if it is 0, no, we should first negate it, because if it is 0, we want to load this instruction directly to register. Not directly, but we have to pass, well, if it is 0, it doesn't matter, we can pass it directly inside this A register, right? So this control bit, so I might have to revert, where is it? Let me guess what I want to do. Yeah, it should be the first. Now this should be B. I'm flipping the inputs because so that we don't have to negate this bit. So now if I pass this first bit inside this selector, if it is 0, then it will select the instruction and load it inside this register. And if it is 1, then we'll worry about it later, but we will just get the ALU output and pass it to either, I guess we don't have to pass it to A register. Maybe we'll have to figure out the logic for this control bit later. So for now, let me pass this. But now I'm unsure if this bit is, which bit I should pass it as selector bit. I know it is this bit from this instruction, but I don't know if it is the 0th bit or the 14th bit. Let me check my implementation of set. I implemented a memory chip earlier, and in that here I use 0 to 13 address bits. So let me see what logic I used. Okay, I'm passing address to this end. I pass it to end to get it inside address t. What is inside address? This are 15 bits. Okay, this 15 bits, and I got rid of 15th bit, so it was the last one. Alright, so that means this is the 0th and this is the 15th bit. So let's see, that means I have to pass, this is the 15th bit. It's asked from here 0 1 2, so I have to pass 15 bit to the selector. So and it comes from the instruction, it will be the 15th bit, right? And also we have to toggle this C bit of A register so that we can store this instruction or the value inside this A register. So but we can't directly pass this bit to A register because we will have to change the state of this register depending on the C instructions as well. So well, we'll pass a intermediate variable to this load. So let's see, but in this case we have to flip this bit to 1 when this instruction bit is 0. So I have to get negation of this bit and pass it to this. So it seems I have to get the negated bit anyway. Yeah, let's get the negated bit, doesn't matter. So we'll pass the instruction oops, I forgot the equal to sign. Instruction bit 15 to input, and I will let's call it a reg L for load. Now we have a flipped bit inside a reg L, and we can pass it to this load. So now if this bit is 0, this A reg L will contain 1 and we will passing it over here. But if it is 1, then it will be 0. But we do want to change this value based on, wait, will we be changing the data? A can be over here, right? So I'm trying to figure out if we do change the value of A register inside the C instruction. So if it is 0 1 1 0 1 0, we don't want to feed it to 1, but this can be 1, right? Let me check the slides. Where was it? Destination, yeah, it can be 1. So if this is 1, the destination can be the A register. So in that case so even though the instruction bit is 0, or even if it is 1 and we get 0 inside this, we still have to pass 1 to this based on its destination. So yeah, I guess so let me not call it arraygel. I will call it not int for inverse of the instruction, or not op. Yeah, that will be that. Not op for, because basically this is the op code. This 15th bit is op code, so not op will contain the flipped version of flipped bit of op code. If it is a instruction opcode will be 0, so we will have 1 inside not opcode, and for C instruction it will be 0, right? And now this arraygl will depend upon this not opcode as well as this destination bit. So let's see. Yeah, not all the destination bits, only this first bit. It will depend on this first bit only. So we can do some kind of logic, and this, let me check which bits are this. 3 bits from this instruction. So if the 15th bit is the opcode, this bit is the opcode, this 2 are unused in case of C. So 15, 14, 13, 12, 11. So 0, 1, 2, 3, 4 and 5. So 5th bit is the one we have to worry about in this case. So if it is 0, if this 5th, if it is 5th, right? 0, 1, 2, 3, 4 and 5. Yeah, if it is 0, then if it is 0 and let me try to write it inside my notes. So I have to make a truth table of kind. So here's what I want to do. D1 bit, and we also have this not op bit, right? So if this D1 bit is 0 and not op, let me write the truth table first. 0, 0, 0, 1, 1, 0, 1, 1. Right, and the output will go inside arraygl, right? No, it was arraygl. So if it is 0 and 0, if both of this bit are 0, that means we don't have to store. DL is 0. This should be DL, not D1. If DL is 0 and not op is 0, but I'm confused. Not op is 0, that means it is a C instruction. In that case, this arraygl should contain 0, because we don't need to store anything inside the A register, right? Not op is 0. Let me write it over here. Opcode is equal to 0. That means it is an A instruction. If the opcode is 1, then it is a C instruction. But in this case, not op will have 1, and not op will be 0 in this case, right? So now if not op, if DL bit is 0 and not op is 0, that means it is a C instruction and we don't have to load anything inside the A register. That means we can pass 0 inside A reg L. Now if it 0, DL bit is 0 and not op is 1, that means it's an A instruction, but DL bit is 0. So if it is an A instruction, we do need to we do need to pass. Wait, now in this case, do we even need not op? Let me check. So what if I just use the instruction 15-bit and not op? Let's see which one simplifies it. So yeah, I'm gonna write another column for not op. Should I? Yeah, let's write for op as well. Now in this case, the op will be 1. Here it will be 0 and 1, 0. So first we won't worry about op for now. Let's see if DL bit is 0 and not op is 1. That means it's an A instruction, but see A. So if this bit is 1, that we definitely want this register load value as 1, because in case of A instruction, regardless of DL bits, we want to save the input, right? But now if DL bit is 1 and not op is 0, that means it is a C instruction. It is a C instruction, but we do need to save the value inside A. So in that case, we will have 1 over here as well. Now not op is 1, that means it's an A instruction, so we don't need to worry about this DL bit. In that case, it will be 1. So this load bit should be 1 only when both of these values are, sorry, it should be 0 when both of these values are zeros, or else we have to keep it as 1. And now let's see, if we get rid of not op and just keep op, then for 0 and 1 we have 0, and for all the other inputs we have 1. For 0 0, for 1 1 and 1 0. But if we keep not op, for 0 0 we have 0, but for 0 1 1 0 1 1. So it seems that keeping not off value will simplify the process. We won't have to So it will be just a basic AND gate. So for 0 0, so this is basically the truth table of AND gate if we keep DL and not OR. So for 0 0 we will have 0 as the output. For all the other cases we will have 1. Oh wait, it is not AND, it is OR gate. So if we keep not off value, we can just use OR gate. So let's do that. So I'm not going to get rid of not off, but I'm going to use an OR gate. And the first input will be, yeah, it will be the instruction bit number 5th, 0, if this is 0, 1, 2, 3, 4, and 5th. I'm just writing the code and I'm not even testing the code, so I'm sure this is going to be a hell when it comes to debugging. Let's roll with it anyway. Wait, this should be a not in, what the hell, a instruction. Now for B we'll pass not off, and now the output will go inside a reg, right? So this is cool. Now if we check the, where is it, we have this control bit and this control bit as well. Now let's see what we want to do. We have these two control bits taken care of. But now we need to take care of this other bits when it is a C instruction. So yeah, let's do that now. So if this control bit is 1, that means it's a C instruction. Now in that case, what do we want to do? We can get rid of these 2 bits, but this bits represents, they are the control bits of the ALU, right? So these are all the bits, so I guess that it will be easier to implement these control bits. We are direct, so in figure we are directly passing all this, so they are in total 6 control bits, and inside this ALU we also have 6 control bits. I'm going to pause the webcam because I'm getting a call on my cell phone. All right, let me get back to where I was. So I was saying, okay, we have 6 control bits inside this six control bits for the ALU ZX NX. So we have to check which bits are we going to pass to this corresponding bits. So for that, what's the chapter about ALU? Sequential memory units, counters. Yeah, it is inside this chapter. Okay, where is it? ALU. ZX, NX, ZY, NY, F, and NO. Now, what does this represent? Okay, ZX is when we want to store 0 inside this X, when we want to zero out the X variable. So let me check this. I have to check the corresponding logic for this bit, so it should be inside. Yeah, it is over here, the computation bits. So if this bit is 0, we are going to do this kind of computations. If it is 1, this computations, and this bit selects the different computations. Now let's see. If this bit is 0 and this is the instruction, then we will basically, what we will do, we will zero out the destination, right? Wait, this is going to be a bit challenging. There's a lot going on inside this, so let me see. We are passing D register as one input and mux. What's the figure? 39. We are passing one input as the D register and second is the mark 16. Now let's see if this is A and these bits are like this, then what do we want to do? What's it? If ZX is 0, then first input will be zeroed out. if nx is 0, oh wait, if zx is 1, then we will have 0 inside x, then we zero out this. Presetting x, presetting y, selecting between plus or and, which is addition or ending, and post setting, negating the output, and this is the output. So what is the difference between this set of instruction and this set? Let's see. This instruction works on memory, so we have am inside this instruction but no am inside this instruction. So what does that mean? And what is this am? It is the memory. It will have the memory of, so m in m. This am will have the value which is being value of the RAM register, which is being pointed by this a. Right. So if a is equal to 1, then we will need to take care of m as well. But if it is 0, now let's check the which should we check? ALU. A register will have the value of m. Then input 1 from the D register, input 2 from either A register or data memory, control bits. Okay, well, let's first figure out what this and this control bits should be. So this D register, it is just a data register, and the only input it is receiving is from this output M. Now we want to store value inside this D register only when, let's see, in case of A instruction, you don't need to touch this D register, right? But in case of C instruction, and in that also, and we have D inside this instruction. What does that mean? Either D registered inside the destination load bits, or it is inside this ALU control bits. In that case, we want to toggle this register. When is that? So it is in this case, basically when the destination bit contains the D register, then only we need to toggle the load bit of D register, right? So where are we selecting? So these are the destination bits. Okay, perfect. So we are selecting D register in this case, and in these two cases, in three cases. And in all of these three cases, which value represents the D register? So in these three cases, the DL bit is 0 1 1, D2 bit is 1 1 1, and D3 bit is 0 0 1. Oh wait, we are also selecting D register in this case. Okay, as you I can see clearly that this D2 bit is 1 only when we are working upon this D register, or at least we have this D register inside this destination, or this destination, either inside this destination or yeah, this destination. So if it is 1, if D2 is 1, then we need to toggle the load bit of D register. If it is 0, we don't need to touch the D register, right? It is 1 in this case when we are storing it inside D register. It is 1 in this case when we are storing it inside D register and RAM. Here also we don't have D. Here we have D and D. So yeah, we can directly pass this bit, this particular bit, to load bit of this D register. So over here we can pass instruction bit. Now this bit is, this was fourth one, so fifth one. This is 4, 0 1 2 3 and 4. Awesome. So we have taken care of this control bit. Now let's take care of this Mach 16 control bit as well. It is also of 1 bit only. Now we are either taking the A, so this bit, this control bit will select what input we will pass as this Y, right? So on what bits will this value depend? And this Y will either have the value from A register or input M. What is input M? It is so this Y will be either value from A or value from a RAM which is pointed by this A register. Cool. So now when should this value be A register or the value of RAM? It will depend upon, well, if the instruction is 0 or if it is of type A, we are not doing any computation, right? But if it is of type, yeah, that is for ALU is for computation. So if it is a C type instruction and this control bit will depend upon, let's see, the destination load bits. Well, not so much. So this control bit will depend upon this ALU control bits. Now what does this ALU control bits signifies? These are the control bits. If A is equal to 0, we have this computation. If A is equal to 1, we have this. Wait, there is a clear distinction. In this computation we are using the value of A, and in this computations we are using the value of M, right? So if A is 0, we are working with the address register. We are computing the address register value. and when a is equal to 1 we are computing the m values. So we can directly pass this a, which is this bit, to this selected bit. Let me see. So if this bit is 0, then it should give the value of a register. If it is 1, it should give in m. 0, address, 1, code. So we can directly pass this. Now where is it? If this is 15th, right? 15th, 14th, 13th, 12th. So we can pass the 12th bit. To this box. Awesome. So now we have this control bit taken care of as well. This one as well, this one as well, and this one. Now we need to take care of this control bits, ALU. So that's the hard part. So let's see. We have used up this control bit, so I guess that leaves us this 6 control bits. Well, yeah, and in this case we have 6 control bits as well. So either they correspond one on one, or maybe will have to perform any kind of logic. So if we check the implementation of ALU, this ZX and NX preset the X value, and ZY and NY preset the Y value. It either zeroes it out or negates it. And F value is for either addition or AND operation. So this one is zeroing out, this one is setting as 1, negating it. Let's see, when do we need to zero out the value of A register? Not A, but when do we need to preset the value of this X? So this is what basically this ZX and NX2. T register will have the data value, right? We are selecting or presetting the value. We need to zero out the value of D. Or negate it. So we are negating it in this case. Right? Wait, you should be checking out these values directly. 0, 1, minus 1, x, y. Of course, so these values correspond directly with these values, right? 0 and 1, minus 1, x. 0 and 1, minus 1, x. So in this case, as x, we have d. After this, we have y. It is either a or m. Of course. And we are selecting it based on this control bit. If it is either A or M. And again, not X, so not T, not Y, so not A or not M. So this table corresponds directly with this table. So let's see how we can use that. Okay, if this table corresponds directly with this table, that means this control bits directly corresponds with this control bits as I guessed. So that means ZX bit is this one, C1, ZNX for bit is C2, and so on. So yeah, I was correct. Okay, these values correspond directly. So that means now let's see. NO correspond to C6, and C6 is 0, 1, 2, 3, 4, 5, and 6. It is the sixth bit, so this should be 6. And F correspond to 7th bit, and Y to 8th, Z, Y 9th bit, and X 10th bit. This should be 11th bit. Now we also need to take care of ZR and NG. So what do they do? ZR and NG, they are basically control bits for if output is equal to 0, then ZR is equal to 1, else ZR is equal to 0. Okay, so well, we don't need to provide the input to it, but these bits will provide the output based on this output value. So if it is 0, then we have this ZR is equal to 1. If output is less than 0, then negative bit, which is NG bit, will be 1. So in that case, and we are going to use this values inside. Let's see where we are going to use it. Here the control output is the output negative, is the output 0. Yeah, so what do we do in those cases? Okay, with these two bits correspond with the program counter, and yeah, that is what we are going to see next, the program counter. Of course, because yeah, so this bits ZR and NG, ZR means the output is 0 and NG means the output is negative. Now we can use those in conditional jumps, and it is the property of program counter to provide the conditional jumps. So yeah, we will store ZR inside, let's see, ZR, I guess. I hope we can use it. And NG inside NG only. Awesome. And now we need to take care of this program counter. What is it? It's over here. We have a load instruction inside program counter, increment, rearrange, etc. Now this load instruction will depend upon, where is it? I have incremented and the load. Wait, I forgot a semicolon over here. This control bit load will depend upon, it will depend upon the jump. If we are doing any kind of jump, then we know basically need to load a different value. Right? And so if the program counter is equal to 0, no jump, PC plus plus, no jump, go to, PC is equal to A, go to, and if condition, else PC plus plus. So this case is being taken care of by this reset bit, right? PC reset is equal to 0. True. But we need to take, so now if it is either go to or conditional go to, we need to toggle the load bit. And if only if the condition is true, we need to toggle the load bit in this case. But in case of unconditional jump or unconditional go to, we need to toggle bit. We need to toggle this load bit as well. And this reset increment bit should be 1 in no jump. So if we are not providing any jump instruction, then it should be 1. And again, in case of conditional go to also, if the condition is false, then we need to toggle this bit to 1, or else it should remain 0. So, and this will depend upon, let's see, just last 3 bits, 0 0 0 0. Wait, but this last 3 bits only tells us what conditions to use, if we should jump or not. If all of these bits are 1, then we need to jump. If all of these bits are 0, we don't need to jump. That means the load bit should be 0 in this case and 1 in this case. But these are all the unconditional jumps. That means the load bit will depend upon the result of this, and the result of this we are getting inside this ZR and NG. when output is equal to 0, we will get to know if output is 0 based on this ZR bit, and if output is less than 0 based on NG bit. But how will we figure out if it is greater than 0? Let's see. Well, I guess I'm going to take a break right now for lunch, and I will get back to the implementation of program counter later. Alright, so stay tuned guys, I will be back after a break. Bye bye.